All right, so welcome to part 2 of 4.1, orthogonality of vectors and subspaces. I've written the important restriction up on the board, and this video is definitely going to be much shorter than the part 1, and hopefully part 3 will also be around this length, because we're going to really kind of focus on just underneath example 1. You'll see this box in the book on page 145, where if V and W are orthogonal subspaces in Rn, then the dimension of V plus the dimension of W has to be less than or equal to n. In other words, we can never have dimensions that add up to something greater than the dimension of the space we're in when we're focusing on the orthogonal subspaces of that original vector space. And so I think one of the examples, we saw this alluded to in part 1 when we were looking at the row space and the null space. He gives a great example, I think. So if you're in a room, and we've referenced this a lot of, this space in your room is R3. So if I think about R3 being our space in this definition, I want you to focus on one of the walls and then focus on one of the floors. And you would make the argument that the floor and the wall are perpendicular to each other. So that any space, if you were to treat the floor as R2 and this wall as R2 as well, that these two spaces should be orthogonal to each other. And what's interesting in terms of this restriction is that if we approach it that way, this wall would also have a dimension of 2. This floor would also have a dimension of 2. They're both planes. But that can't exceed 3, so that wouldn't work. Because if both planes essentially create this 3D space that I'm in, think almost like an X and Y and Z axis, that can't happen based off of our restrictions. We can't add two spaces, orthogonal spaces, and get something greater than, again, the dimension of the space we're in. So the question kind of arises, okay, well, what's wrong with this? And the answer is fairly simple, which is they must have something in common that's not orthogonal, because the only way for two spaces to be orthogonal is if every vector in each space is orthogonal to each other. And the book, again, points this out if you read it, but and I know you can't see the floor, but if you think about where the wall and the floor meets, there's a line that's formed there in space. And that line is a line that is in both planes, and it's not orthogonal because it's the same vector. And so this wall in R2 and the floor in R2 share a common vector. They can't be orthogonal spaces, and so it doesn't actually break this rule. And so it seems just kind of weird. Like, again, you think this space of a floor and the space of the wall, if they meet at 90 degrees, that they'd be orthogonal spaces, and they're not. And it's because they share that common point. This line going all the way down to the left and right. And so where this gets interesting then is now asking the question, okay, well, what if we do have just two subspaces that aren't necessarily less than n, but are truly equal to n? In other words, they add together and give us the entirety of the space. And if we have two subspaces that are orthogonal that do this, we say that they are orthogonal complements. So for example, if I have a subspace V, then I would notate the orthogonal complement with V and then the perpendicular symbol. And so again, if I have two spaces here, instead of calling this W, I would just call this the complement if I have equality here. And we saw this. If you think back to the 4 fundamental subspaces, and at the very end of that video, we added up the dimensions of the spaces. It was equal to the dimension of the entire space that those subspaces lived in. Again, for example, as a reminder, or not an example, but just as a reminder, when I'm looking at the row space and null space for a matrix A, both of these are subspaces of Rn. And if you remember from the fundamental theorem of linear algebra part 1, that the dimension of the row space is equal to the rank, well, the null space is n minus the rank. And so if I add these two things together, we get n. That means that's the entirety of Rn. The dimension of this space and the dimension of this space, and if these are orthogonal, which we've shown that they are, they're orthogonal complements. They give us the entire dimension of the space that they're in. If we take this to the column space, excuse me, in the left null space, we see the same thing happen, but this time for Rm. These are subspaces of Rm, where R plus M minus R would then give me M. And these are orthogonal subspaces. So because they give us the entirety of this space, we can say that they're orthogonal complements. And what we're going to see when we start looking at the basis for this stuff is that because they're orthogonal complements, they add up. If I was to take a vector from here and a vector from here, they can essentially create every vector in this space of Rm because they're complements. Every vector in these spaces, respectively, can be rewritten or expressed in terms of their components, their complements, bases, vectors that are in the basis of these spaces. And that's the purpose of part 3. But what we essentially have then is, and I'll leave this in the textbook and not write this up on the board, but that the null space is the orthogonal complement of the row space because of putting these definitions together. The left null space is orthogonal complement of the column space because it creates all of these spaces. And so these definitions then fit together, and we have now found some more properties between these 4 fundamental subspaces. Again, in part 3, we'll take a look at an example of for the basis of these subspaces and how essentially we can combine them to form any vector in these respective spaces.